Hello guys, welcome to the world of STEM. I am Amrit Vignesh, and today we'll be going over a chemistry topic known as stoichiometry. So I'm going to give a quick overview over stoichiometry, and stoichiometry is involved in all levels of chemistry. Your honors chemistry, which is probably the first chemistry course you take in high school, AP chemistry, most college courses will have to use some application of it, even though it will be considered prerequisite college knowledge. Stoichiometry is a subfield of chemistry that talks about the relationship and the qualities of certain reactants and products in a certain reaction, which can be established by the mole ratio of the Balanced equation. And I will tell you that I will explain more about the mole ratio more in depth. But the first thing we have to see is it talks about the equation being balanced. So an equation, and this is hydrogen gas and oxygen gas reacting to make water in its liquid form. Now, remember, water can also be in a gaseous form. Now, the problem is this is not unbalanced. As you can see, there's two hydrogen on the left and two hydrogen on the right, so that works out. However, there's two oxygen on the left and only one oxygen on the right. So we have to balance this equation. Now, how do we do that? It's not written up here, but I can explain to you verbally. Because we have two oxygen on the left and one on the right, let's just experiment by multiplying the right by 2. That gives you 4 hydrogen now on the right and 2 oxygen on the right. So that oxygen is satisfied, but now that hydrogen coinciding, when they were both the same, that's now contradicting. So because we have 4 hydrogen on the right, we have to also multiply the H2 by 2. Balance equation. 2 times H2 plus O2, and both in their gaseous form, is 2H2 on its liquid form. Now the mole ratio is just whatever is the coefficient of these compounds, of these substances. So as you can see, there's 2 moles of hydrogen gas reacting with 1 mole of oxygen to create 2 moles of water. And this mole ratio will be important in the field of stoichiometry. So let's do an example. We're given the same equation that I just talked about, and as you can see, it's an unbalanced form. Now, a lot of people make the mistake of going off this without balancing, but balancing the equation makes sure that your mole ratio is right. 25 grams of hydrogen gas and 200 grams of oxygen gas react together to form a certain amount of H2O. And we have to find a certain amount of water that is created. Now, this is actually a little bit of a harder stoichiometry example than what you'll see first. Usually, you'll just be given one reactant, so you'll only get one answer. But by this, because we have a relationship between hydrogen gas and water, but we also have a relationship with oxygen gas and water, we're going to get 2 answers. And we'll address how you can approach these 2 answers. First, we're going to balance the equation, and that gives you 2 times 2H2 plus O2 is 2H2O. Now, first step I'm going to go through is how we can get from grams of H2 to grams of water. We're given that there's 25 grams of hydrogen gas. In stoichiometry, everything is converted to moles as we're using mole ratios to set up how we can relate the mass of one reactant or product to another reactant or product. So here, the molar mass of hydrogen gas is 2.016. Now, I'm not using a significant digits that much in this, but I was just rounding out to general values. Significant figures may be required by the teacher and go based off that. Now, if you see 25 grams of H2 and 2.016 grams of H2. So as you can see, the grams of H2 cancel out with each other. And I can kind of show that. As you see, this grams of H2 and these grams of H2 cancel out. Now, this part alone is just getting our moles. Now we have our mole ratio. The mole ratio is what is given by the balanced equation. And if we saw in the balanced equation, there's 2 moles of water and 2 moles of hydrogen gas. These, of course, so this moles of H2 now cancels out with this moles of H2. Okay? Now we have how many moles of H2O we have now, because we have established that hey, we have this amount of H2O, so we must have this amount of H2O by the mole ratio. But we still want to find the amount of grams. So finally, we're going to convert that moles to grams using our mole ratio, our molar mass of H2O. And these cancel out. So all we have left is grams of H2O. And that gives you 223.4 grams of H2O. Same goes here. And I'm not going to, so as you can see, we have 200 grams of O2. And remember, this is the one where I said we're going to have two answers, which is not actually common in this simple stoichiometry problem. But I wanted to show how we can do this in just one example. Because in the end, this is just kind of related. So we could say 200 grams of oxygen gas. We can convert it to moles using our molar ratio, which is 31.999 grams. Now our mole ratio here is not 2/2, but it's actually 2 moles of H2O to 1 mole of oxygen gas. And that was given in the equation, as you can see, the coefficients of those reactants and products. And then we can once again use the mole ratio. And you get 225.2 grams of H2O. And you may be like, hey, these are pretty similar. And yeah, I did kind of make the problem to be in that way. But we have two answers, two productions of H2O. So what is our answer? Two different results means that we'll have to use the lower amount. So in this case, we're going to be using 223.4 grams of water. And the reactant that produced that amount, so in this case that was hydrogen gas, is known as a limiting reactant. While the other one, which is oxygen gas in this case, is the excess reactant. So, as I said, hydrogen gas is the limiting reactant, while oxygen gas is the excess reactant. Now, that excess reactant, you may be appealed by its name and saying excess. And you want to hear, like, what is excess? Because the limiting reactant basically limits the amount of H2O that can be produced. But we still have that excess reactant. Now, how much excess is available after the reaction completes? So all the because hydrogen gas is the limiting reactant, it's all used up, but we still have a little bit of oxygen gas that hasn't gone to reaction yet. I mean, that is the excess. So we have to kind of go back. We have to use you have to use the smaller value that we got, which was 223.4, and convert that grams of H2O to grams of O2. So it's like going reverse. And once again, we can use it where we convert grams of H2O to moles of H2O. Then we use the mole ratio to find moles of O2. And then we can find grams of O2. And you get 198.4 grams of O2. However, what we used originally was 200 grams. So it's only saying that 198.4 grams of O2 was actually used in the reaction. The amount of excess reactant is the original 200 we had minus the 198.4 grams of O2 that we actually used. And that gives you 1.6 grams of O2 excess. Now, let's pretend that we performed a reaction. So we did this actually, instead of just doing theoretical, we actually performed a reaction between hydrogen gas and oxygen gas to produce water. Now, we are given that 200.0 grams of water is produced. And we're like, hey, it did say that we should get 223 point, I believe it was 2 or 4. It was one of those, but it said we got that. But why is it only saying we have 200? Well, obviously these reactions have a lot of errors associated with them. It can be a human error. It can be errors with general errors with measuring. It's never going to go to complete reaction when you see experimentally. And therefore, there was a measure made to compare that experimental value to the theoretical value. Percent yield. So your percent yield is your actual yield over our theoretical yield times 100%. So we see here, we got 200.0 grams divided by the actual, so that's our actual yield, divided by our theoretical yield, which was 223.4 grams, which is what we should have got. And we're going to times that by 100%. And we see that our percent yield is 89.5%, which is actually pretty decent considering it was an experimental reaction. I mean, 89.5% is pretty good. So we're going to have some extra applications of stoichiometry. And I'm not going to go over it in this video, but stoichiometry can be used with the ideal gas law. An ideal gas law is, I didn't write it here, but I will. It's basically something relating the pressure, volume, amount of moles, in temperature of an ideal gas. So ideal gas is under few conditions which you can research on your own. So if we're given the pressure, temperature, and volume, we can find the moles, and therefore we can do some stoichiometry calculations based on that. So this will not be analyzed, but when you get to that point of chemistry, you'll definitely revisit the idea of stoichiometry when you talk about ideal gas. Watching. Remember to subscribe to the World of STEM, and see you in a few weeks. Thank you.